specific heat capacity. In that, first one, heat capacity. Heat capacity, let us denote that by capital S. Heat capacity of a substance is the quantity of heat required to raise the temperature by 1 Kelvin. Now let us understand this statement. If this is a body of some mass and this is at 20 degrees Celsius, to increase the temperature from 20 degree to 30 degree, let 100 joule is required. Okay, so by supplying 100 joule of heat, temperature is raised from 20 to 30 degrees Celsius. Now let us increase the temperature from 20 to 40 degrees Celsius. In this case, the amount of heat required is say 200 joule. In order to define heat energy required per Kelvin is suitable. That is, if this body temperature is increased from 20 to 21 degrees Celsius with the supply of say 10 joule, then 10 joule per Kelvin is the heat capacity of the substance. So for the sake of definition, we consider 1 Kelvin rise, 1 Kelvin rise in temperature, 1 Kelvin rise in temperature, or 1 degree Celsius rise in temperature. Temperature is 20 degrees Celsius. Then temperature in Kelvin scale is 20 Kelvin. No, this is not true. 20 degrees Celsius is not equal to 20 Kelvin. You know, because temperature in Kelvin scale is 273 plus temperature in Celsius scale. So we have to add 273 to this. Whereas temperature difference equal to 20 degrees Celsius. Temperature difference delta T. Then delta capital T is equal to 20 Kelvin. This is right. Temperature difference in degree Celsius is equal to temperature difference in Kelvin scale. But individual temperatures are not same. In that sense, 1 Kelvin rise in temperature is equivalent to 1 degree Celsius rise in temperature. Okay. Now, heat capacity is heat supplied divided by rise in temperature. Let us denote heat supplied by delta Q. Delta Q is the heat supplied. Rise in temperature is delta capital T. Heat supplied to change in temperature. Can you guess the SI unit of heat capacity? Numerator is joule, denominator is Kelvin, isn't it? So it is joule per Kelvin. Joule per Kelvin. Now, specific heat capacity. Specific, it is defined with respect to 1 kg. Specific heat capacity is the quantity of heat supplied to raise the temperature of unit mass of a body by 1 Kelvin. 1 kg mass by 1 Kelvin. Let me consider this body of mass 1 kg and this is at 20 degrees Celsius. To increase its temperature to 21 degrees Celsius, we have to supply heat energy. So this symbol represents heating. This downward upward arrow mark represents heating. Okay. So after heating, temperature is increased from 20 to 21 degrees Celsius. For that, heat energy required is delta Q equal to say 150 joule. Let me make it clear. 1 kg is at 20 degree. By heating, its temperature is increased to 21 degrees Celsius by supplying 150 joule. Then specific heat capacity of this body is said to be 150 joule per kg per Kelvin. So specific heat capacity or simply specific heat of this object is 150 joule per kg per Kelvin. Let us denote specific heat capacity by small letter s. It is heat supplied divided by rise in temperature into 1 by mass, means per Kelvin for every degree change in temperature. And SI unit of this is, or equation of this is 1 by mass into delta Q by delta T. So this is specific heat capacity, specific with respect to mass. One more observation. Heat supplied by rise in temperature is heat capacity. So specific heat capacity equal to 1 by mass times heat capacity. So I can write specific heat capacity equal to this is heat capacity, capital S, divided by mass. So heat capacity per unit mass is specific heat capacity. So this can be asked for 1 mark. Write the relation between heat capacity and specific heat capacity. In terms of statement, specific heat capacity is heat capacity per unit mass. Heat capacity per unit mass. Molar specific heat capacity. Same statement, but this molar specific heat capacity is defined with respect to 1 mole. Earlier it was with respect to 1 kg, now with respect to 1 mole. Go through this statement. Molar specific heat capacity is the quantity of heat supplied to raise the temperature of 1 mole of a substance by 1 Kelvin. Earlier 1 kg, now 1 mole. Let us denote molar specific heat capacity by C. C equal to 1 by mole heat supplied by rise in temperature. So 1 by mole, 1 by mu. Mu stands for number of moles, mu, into delta Q, heat supplied by delta T. Delta Q by delta T. So SI unit of this is 1 by mole heat supplied joule per mole per Kelvin. Joule per mole per Kelvin. This is specific heat capacity, molar specific heat capacity. Now as an example, let me consider carbon 612. Carbon 12. 6 is atomic number, 12 is mass number. So these things you will learn in chemistry classes. So there your understanding level will be much better. As an example, let me take this. Carbon 612. This is atomic number and this is mass number. Mass number. Okay, fine. If carbon 12 is used, then consider 12 kg. 12 kg of carbon 12. And 12 kg of carbon 12 is 1 mole. 1 kg mole. Since we are using SI unit, so amount of heat required to raise the temperature of 12 kg of carbon by 1 Kelvin. Nothing but 1 mole of carbon by 1 Kelvin is this molar specific heat capacity of carbon. This is how we have to use molar specific heat capacity. Molar specific heat capacity at constant volume, denoted by CV. In the case of gases, temperature, volume, pressure, these are the parameters, variables. If you change temperature, volume also changes, pressure also changes, isn't it? So it is difficult to monitor both simultaneously. That is why we keep volume constant and see how temperature affects pressure. And this type of specific heat capacity is called specific heat capacity at constant volume. Molar specific heat capacity at constant volume. Similar statement but small change. Observe, it is the quantity of heat supplied to raise the temperature of 1 mole of a substance by 1 Kelvin, same as before. At constant volume, we have to include this. Only change in symbol, 1 by mole into heat supplied by raise in temperature. Students, you have to make a note of heading, statement, equation, and then this 1 by mole is 1 by mu, number of moles, into delta Q by delta T. So this is molar specific heat capacity at constant volume. Next, let us keep pressure constant and see how volume changes with respect to temperature. And that is going to be, yes, molar specific heat capacity at constant pressure. Molar specific heat capacity at constant pressure, denoted by Cp. It is the quantity of heat supplied to raise the temperature of 1 mole of a substance by 1 Kelvin at constant pressure. Cp, only change in symbol, 1 by mole into heat supplied to rise in temperature, equal to 1 by mu, just like before, delta Q by delta T. Joule per mole per Kelvin. SI unit is also same. Joule per mole per Kelvin. This is molar specific heat capacity at constant pressure. In next chapter or the kinetic theory of gases, you are going to learn more about Cp and Cv. For time being, this is enough. Only statement, equation and SI unit. Okay. Specific heat capacity of water is about 4200 joule per kg per Kelvin. I said about. Okay, that's enough. Compared to most of the liquids commonly available or frequently available liquids, water has very high specific heat. Because of that, there are many applications. And one such is, water is used as a coolant. So if you want to cool down some object quickly, easily, then the most frequently used coolant is water. When there is fever, we put cloth soaked in water on our forehead, isn't it? Because it absorbs more heat energy, but the rise in temperature is little. To cool down hot milk, if we are in a hurry and hot milk is given to us, then to cool it down, we keep it in water bath. Why water bath? Means it absorbs more heat energy, but the rise in temperature of that water is less. Now the question comes, can't we use oil? Certainly we can use oil, but oil is messy, right? At the same time, oil is costly. So that is why the most abundantly used coolant is water. One is its price, second, availability, third, its very high specific heat. Water warms up more slowly than land during summer. True. If this is a water body, this is water and this is land. So during summer, sun rays will heat water as well as land. Our temperature of land is very high compared to temperature of water. That's because specific heat capacity of land, mud, soil, stone, gravel, whatever it is very low compared to specific heat of water. Therefore, rise in temperature of water is less. Wind from the sea has a cooling effect. True. Let us understand this in the next topic, that is land breeze and sea breeze. Because of very high specific heat capacity of water, sea water temperature rises very little, whereas temperature of land increases to greater extent. So as a result, there is cooling effect from the sea. Time being, this is enough. In the next topic, let us go through this in detail. Earth's surface warms up quickly during the day and cools quickly during the night. True. So land after absorption of heat is heated quickly because of very low specific heat. At the same time, during night times, it cools down faster than water. Water takes more time to cool down. Again, what is the reason means? High specific heat capacity. Calorimetry. Calorimetry is measurement of heat. It's a branch which takes care of measurement of heat. Calorimeter is a device used to measure heat. It's an arrangement where we can use that arrangement to measure heat. That is a calorimeter. So this is for 1 mark and this is also for 1 mark. Principle of calorimetry. So what is the principle behind measurement of heat? That is nothing but principle of calorimetry. Metry is measurement. In an isolated system, heat lost by a body at higher temperature is equal to heat gained by a body at lower temperature. Now, let this be an isolated system. Isolated systems are represented by double wall, insulating wall. Okay. Now, let there be hot water. Hot water at 80 degrees Celsius. This hot water is mixed with cold water. Cold water at 20 degrees Celsius. Isolated system. Hot water can lose heat energy. At the same time, cold water can gain heat energy or absorbs heat energy. So heat lost by hot water is equal to heat gained by cold water. Heat lost by this is equal to heat gained by this. That is the principle of calorimetry. If there is any loss of heat, then we cannot claim that heat lost by hot water equal to heat gained by cold water. Thereby, there will be error in the measurement of heat. So that is why, to reduce the error, we have to properly insulate the system. And that is the principle of calorimetry. And this is also asked for 1 mark. Important question. Mention the principle of calorimetry. This is a simple calorimeter used in our laboratories, 11 standard laboratories, isn't it? Or similar type you might have seen. There is a wooden container, wooden box. Inside this wooden box, there is a copper vessel. If this is the wooden box, then this is the copper container. between wooden box and copper container, there is insulating material to prevent loss of heat. To prevent loss of heat. Okay. Of course, there should be a lid. Let me write the lid. That lid is this. 2 holes are provided in this lid. Through those 2 holes, one hole is utilized for thermometer. And the other hole, there is a stirrer. So this is the stirrer, the one which is used to mix. In kitchen, we use spoon as stirrer, isn't it? So in this case, copper stirrer is used. So this copper container, stirrer and thermometer should be properly insulated. So this is this arrangement. And you can see a stand. This stand is used to support thermometer. Okay. So this is a typical calorimeter. There can be slight changes in the design, doesn't matter. And you may use or you will use this calorimeter in your laboratory. Wooden box, copper vessel, and this is the insulator, insulating material. This is the stirrer and thermometer. Thermometer, to support the thermometer, this stand is used. This is also called Joule's calorimeter, one of the simplest type of calorimeter. Now, few statements. Change in state. Change of state from solid to liquid is called melting. You have studied this in lower classes, lower standards. The temperature at which solid and liquid states of the substance are in thermal equilibrium. Solid and liquid states is called melting point. Melting point depends on pressure. Melting point means it is that temperature where the change in phase occurs from solid to liquid, isn't it? There is one more statement for melting point. If this is a container, this is ice. Because of heating, if ice starts melting, so melting of ice at standard pressure takes place at 0 degrees Celsius, isn't it? So part of ice is in liquid state now. So this is water. So this is water. Now at 0 degrees Celsius, ice and water will coexist, means they will exist together. And temperature of ice equal to 0, temperature of water is also equal to 0. If these two temperatures are same, then we say that they are in thermal equilibrium. Earlier statement, it is that temperature where the change occurs from solid phase to liquid phase. Now one more statement, it is that temperature where solid and liquid coexist at thermal equilibrium. And melting point of ice depends on pressure. As pressure increases, melting point decreases. Okay. Let us see few applications of this beautiful concept. Melting point depends on pressure. Rigidation, important for 1 mark. Rigidation is the phenomenon of the ice melting under pressure and refreezing when the pressure is reduced. Ice melting point is 0 degrees Celsius at standard temperature, standard pressure. Standard pressure means 1 atmospheric pressure. Time being, neglect standard pressure, and to understand this is sufficient. At 0 degrees Celsius, ice melts. Now, when we apply pressure on the ice, then at the region where pressure is high, melting point decreases. As a result, that ice goes to liquid state. And if you remove that pressure, since that water is already in contact with ice, that water again refreezes. That refreezing concept is called rigidation. An example for rigidation, beautiful concept, ice skating. In ice skating, what happens? This is ice. This is the knife edge of the shoe. And this is the knife edge. At the point of contact, all along these points, pressure increases. Weight of the person, weight of the shoe, weight of the dress, everything will be acting down. So at the region of contact, pressure increases. Pressure increases, melting point, let me write MP, melting point decreases. Now there is water here. So there is formation of water. This skater or this skating can slide on water. Whenever there is water between two contacting surfaces, then water behaves as a lubricant. Friction decreases. It can slide. One object can slide on the other object easily. So he can easily slide. He can skate. When he goes further, then this melted water will be in contact with ice. So this ice refreezes. That refreezing is rigidation. He is going further. Again, pressure at this region decreases, increases, melting point decreases, ice becomes water. He will be skating. That water is again in contact with ice. That again refreezes. So when the skater is moving, so he leaves behind a trail of water, and that water again refreezes. And this is rigidation. Let us observe carefully. Look at the knife edge. This is water as well as small ice particles. See marking. After some time, that becomes ice, rigidation, and that marking also vanishes. So this is rigidation in the case of ice skating. Rigidation, one more example is wire sinking through ice. Okay, simple and small experiment. This is ice. This is a wire, and the wire, ends of the wire are connected to two masses. So basically we are trying to pull this wire down. So we are trying to pull this wire down through these two weights. Now at the region of contact, here the pressure increases. Because of weights, force by area, pressure increases. Pressure increases, melting point decreases. As a result, this region becomes water. When this region becomes water, the wire can easily sink into water. Now, this is the position of the wire, and the water above the ice refreezes. That is rigidation. Now, this is again ice. See, there is ice, wire, ice. So the wire is sinking into ice. Again, pressure just below the wire is more, therefore melting point is less. Again, that part of the ice melts. After that melting, the wire further sinks. So this is the position of the wire, and there is refreezing. So this region will become ice again. There is ice, wire, ice. So this refreezing is called rigidation. So wire sinking in ice, just like A knife going through a butter is beautiful example of rigidation. Now a small video clip on wire sinking through ice, an example of rigidation. This video clip is taken from YouTube channel Vaporization. So he is a very famous guy. He does lot of small videos. He puts lot of effort to create all these videos. You can subscribe to his channel and just watch. They are fantastic videos. Weights, ice, and this is the wire. See, wire is sinking through ice. After that, this water becomes ice. See, of course, this is a time-lapse video. Little fast forwarded. Thanks to Vaporization. One more change of phase, vaporization. The change of state from liquid to vapor is called vaporization. Liquid to vapor or corresponding gas is called vaporization. Boiling point, the temperature at which liquid and vapor states of the substance coexist. Now, container, water, let us heat water. At 1 atmospheric pressure, water starts boiling and this is the vapor. And temperature of vapor is 100 degrees Celsius. Temperature of water is also 100 degrees Celsius. This water and vapor are in thermal equilibrium because their temperatures are same and they coexist. So it is that temperature where these two coexist at thermal equilibrium is called boiling point. Sublimation, the change from solid state to vapor state without passing through the liquid state is called sublimation. So beautiful example is dry ice, isn't it? Dry ice, solid state, it goes to vapor state directly without melting. That is sublimation. Camphor, camphor goes from solid state to vapor state without entering the liquid phase. That is sublimation. Latent heat. Latent heat is the amount of heat required to change the state of unit mass of a substance at constant temperature. Now understand this. This is ice. Ice is at minus 10 degrees Celsius. Let us start heating ice. Means we are supplying heat energy. Because of heat energy, temperature of ice increases to minus 9, minus 8 degree, minus 7 degree, minus 6 degree. We are supplying heat energy and this temperature is increasing. When temperature of ice reaches 0 degree Celsius, then there is melting of ice. Ice starts melting. You continue to supply heat energy, you won't see any increase in temperature, but the ice goes from solid state to liquid state. So melting of ice takes place at 0 degrees Celsius. Some amount of heat, delta Q, is required to melt the ice at 0 degrees Celsius. So some amount of heat, joule per kg, heat required per kg is a measure of latent heat of ice. Latent heat of fusion. Latent heat of fusion is the amount of heat required to change the state of unit mass 1 kg from solid to liquid state. Solid to liquid or liquid to solid. So latent heat of fusion is amount of heat required to change the phase of unit mass of a substance from solid to liquid. Latent heat of vaporization. Latent heat of vaporization is the amount of heat required to change the state of unit mass of a substance from liquid to gas. Liquid to gas Earlier, latent heat of fusion, solid to liquid. Now latent heat of vaporization, heat required to take the substance from liquid to vapor, that to unit mass. So we can write latent heat of a substance equal to delta Q by mass. Delta Q is joule, mass is kg. Students, take care of this. It is small letter k. Don't write like this. Okay, small kg. Note, latent heat of fusion 3.33 10 to the power of 5 joule per kg. That's lot of energy. Latent heat of vaporization 10 to the power of 5 22.6 10 to the power of 5 joule per kg. Here is a conceptual type question. Burns from steam is more severe than burns from boiling water. Explain. Boiling water damages the tissue. Steam also damages, but the burns due to steam is severe. The reason is here. Container, this is water at 100 degrees Celsius, and this is steam. This is also at 100 degrees Celsius. If skin is in contact with hot water, 100 degrees Celsius water, then this hot water can supply some amount of heat. It has some heat capacity, so that burns. But steam has additional energy. Latent heat of vaporization is 22.6 10 to the power of 5. Suppose 1 kg of steam is in contact with skin. That steam has an additional energy of 22.6 into 10 to the power of 5 joule. Additional energy, because to go to this state it requires additional energy. That additional energy also falls on the skin. That is why burns from steam is severe than boiling water.